Welcome to this problem-solving session. Today, we'll tackle problem number 186, reverse words in a string 2. This problem challenges us to manipulate strings efficiently while maintaining their structure. Let's dive in and explore the approaches to solve it. In this problem, we are given a character array S that represents a sentence. The sentence consists of words separated by single spaces, and each word is made up of only English letters, which can be lowercase, uppercase, or a mix of both. Our task is to reverse the order of the words in this sentence, but we must do so in place. This means we cannot use any additional arrays or allocate extra memory to store the result. Instead, we need to directly modify the input array S to achieve the reversed order. For the input format, S is a character array, such as T, H, E, S, K, Y, I, S, B, L, U, E, and the output will be the same array, but with the words reversed, like B, L, U, E, I, S, S, K, Y, T, H, E. Let's explore some examples to understand this better. In the first example, the input is T, H, E, S, K, Y, I, S, B, L, U, E. Here, the words are the sky, is, and blue. Reversing their order gives us blue, is, sky, and the. When we modify the array in place to represent this new order, the output becomes B, L, U, E, I, S, S, K, Y, T, H, E. In another example, the input is a B, C, where the words are a B and C. Reversing their order gives C, B, and a, so the output is C, B, a. This demonstrates that the solution must handle reversing all words while keeping the spaces in their correct positions within the same array. Now, consider a third example where the input is H, E, L, L, O. In this case, the input contains only one word, hello. Since there's nothing to reverse, the output remains the same as the input, which is H, E, L, L, O. Moving on to the problem constraints, the length of the array S can range from 1 to 100,000 characters. The array consists of printable ASCII characters, does not have leading or trailing spaces, and maintains exactly one space between words. These constraints help focus the problem, ensuring we only deal with valid, well-formed sentences. There are a few edge cases to keep in mind. First, if the input contains only one word, such as H, E, L, L, O, the output will be the same as the input because there's nothing to reverse. Second, if the input has a minimum length of 1, such as a, there's no reversal required, as the array only contains one character. Third, the problem guarantees that there are no multiple consecutive spaces in the input, so we don't need to handle such cases. Finally, the solution must efficiently handle the maximum constraint of 100,000 characters, ensuring that the implementation is optimized for large inputs. Keeping these points in mind will help us develop a solution that is both correct and efficient. To tackle this problem, the brute force approach gives us an intuitive starting point. The idea here is to split the input array into individual words by identifying spaces as delimiters. Once we have the words, we reverse each one independently and then reassemble them back into the array, ensuring the original order of words is preserved. While simple and easy to understand, this method comes with significant drawbacks. Splitting the array requires additional memory to store the words temporarily, which violates the problem's in-place constraint. Although the time complexity for splitting and reversing is linear, the space inefficiency makes this approach less desirable. It's a good conceptual foundation, but not the optimal solution when constrained by memory usage. Now, let's consider a more optimized approach that adheres to the in-place requirement. Instead of working with individual words right away, we reverse the entire array first. This step effectively rearranges the order of words, bringing the last word to the front, the second to last word to the second position, and so on. After reversing the entire array, we locate each word by identifying spaces as boundaries. Then, we reverse the characters within each word individually. This two-step process ensures that the final result has the correct order of words and the correct arrangement of letters within each word. The beauty of this approach is that it requires no extra memory and operates entirely in place. With a linear time complexity of O, N, and constant space complexity, this method is efficient and well-suited for our constraints. While the optimized approach is highly effective, it does come with some trade-offs worth noting. The implementation is slightly more complex than the brute force method since it requires two passes over the array, one to reverse the entire array and another to reverse each word. However, this added complexity is minimal and manageable. Ultimately, the optimized approach was chosen because it strikes the right balance between efficiency and constraint satisfaction. It achieves linear time complexity, operates entirely in place, and breaks the problem into two straightforward steps, reversing the entire array and then fine-tuning the result by reversing subarrays for each word. By leveraging these simple yet powerful operations, the method avoids the space overhead of brute force while maintaining systematic clarity. The key insight, or aha moment, lies in recognizing that reversing the entire array transforms a seemingly complex word ordering problem into a simpler one. Instead of dealing with individual words up front, this holistic approach allows us to solve the issue of word order in one pass and then focus on reversing the letters within each word in a second pass. While alternatives like the brute force method are intuitive, they fail to meet the in-place requirement. Other in-place algorithms that involve manual character shifts can add unnecessary complexity and overhead. The optimized approach, on the other hand, balances simplicity and efficiency perfectly, making it an ideal solution. By combining in-place operations with a linear time complexity, it addresses the problem's constraints while remaining elegant and systematic. Here, we are tasked with reversing each word in a character array while maintaining the order of the words. To achieve this, we break the solution into 4 distinct steps. First, we need to split the sentence into individual words. Starting with a character array, we'll iterate through each character, using a temporary variable to collect characters until we encounter a space. At that point, we add the collected word to a list and reset the temporary variable. Once the loop completes, any remaining characters form the final word, which is also added to the list. This gives us a clear separation of words for the next step. Next, we focus on reversing each word. For this, every word in the list is converted into a list of characters, allowing in-place modification. Using the two-pointer technique, we swap characters from the start and end of the word, moving the pointers inward until they meet. This ensures each word is reversed efficiently, setting us up for the reconstruction phase. After reversing each word, we now have a list of reversed words. The next task is to reconstruct the sentence. This involves concatenating the reversed words with a single space between them. The join method is particularly useful here, as it allows us to combine all the words efficiently without excessive intermediate operations. The result is a reversed sentence in string format. If the problem constraints require us to return the sentence as a character array, we can easily convert this string back into a list of characters. This final conversion ensures the output matches the input format. Along the way, we leverage key techniques such as in-place reversal using two pointers to optimize space usage, and the join method to minimize computational overhead during reconstruction. Together, these choices make the algorithm both time and space efficient, with a linear time complexity of O(n) and a similarly efficient space complexity. It's important to address additional considerations and edge cases. For example, the algorithm handles inputs like a single word without any spaces, multiple words of varying lengths, or even an empty input entirely. Each of these scenarios is resolved seamlessly due to the design of our steps. The choice of data structures also plays a crucial role. The character array allows us to maintain the problem's constraints, while the list of strings serves as a temporary storage for words during splitting and reversal. The two-pointer technique ensures that each word is reversed in place with minimal overhead. For complexity, we achieve O(n) time since splitting, reversing, and reconstructing all operate linearly with respect to the input size. Similarly, space usage is linear, as we store intermediate structures like the list of words and the reversed sentence. These considerations ensure the algorithm is robust and efficient across a wide range of inputs. Now, let's look at the pseudocode to consolidate everything we've discussed. We begin by iterating over the input array to split it into words. Each character is added to a temporary list until a space is encountered, at which point the accumulated characters are joined into a string and appended to the words list. After processing all characters, any remaining characters are added as the final word. Next, we reverse each word in the list. This involves converting the word into a list of characters, then using two pointers to swap elements from the start and end until they meet in the middle. Once reversed, the characters are joined back into a string and replaced in the list. After reversing all words, we reconstruct the sentence by joining the list of reversed words with spaces. Finally, if required, we convert the reconstructed sentence back into a character array and return it. This sequence of steps ensures correctness and efficiency. Let's walk through an example to see the algorithm in action. Consider the input character array THISISTEST. First, we split this into words, resulting in the list "This is a test." Next, we reverse each word individually, producing citing, say, a set. Then, we reconstruct the sentence by joining these reversed words with spaces, which gives the string citing set. Finally, if needed, we convert this string back into a character array, resulting in the output SIHTSIATSET. This step-by-step process demonstrates how the algorithm handles the input to produce the desired result, adhering to both the problem's requirements and constraints. The code implements a solution to LeetCode problem 186, reverse words in a string 2. The input is a list of characters representing a sentence, and the goal is to reverse the words in place without using extra space for another array. The solution begins by defining a helper function reverse, which reverses the portion of the array between two indices, start and end. This function swaps characters symmetrically from the edges inward until the midpoint is reached. The first step is to reverse the entire character array. This effectively reverses the order of all characters, including spaces, which places the word's characters in reverse order but also reverses their positions. The second step is to reverse each word individually. By traversing the array, the program identifies word boundaries either when encountering a space or reaching the end of the array. Each word is reversed in place using the reverse function, restoring the correct order of characters in that word. The start pointer is updated to the beginning of the next word after each reversal. This approach has a time complexity of O(n), where n is the length of the array, because each character is processed a constant number of times. The space complexity is O(1), since the reversal is done in place without additional storage. The implementation is efficient and adheres strictly to the problem constraints of in-place modification. This is the Java implementation of LeetCode problem number 186. Reverse words in a string 2. The code mirrors the Python logic, using helper methods to reverse parts of the input character array. Key differences include explicit type declarations and use of Java's array manipulation syntax. The reverse words method first reverses the entire array, then reverses individual words to achieve the desired order. To begin, let's look at the simplest case, a single word. Here, the input array represents the word hello as a list of characters. The first step is to reverse the entire array. This is done by calling the reverse function with the start and end indices of the array. During the first iteration, the first and last characters are swapped, resulting in the array becoming O-E-L-L-H. In the second iteration, the second and second to last characters are swapped, updating the array to O-L-L-E-H. The process stops when the start index becomes greater than or equal to the end index. At this point, the entire array is reversed, and it now reads as Allah. After reversing the entire array, the next step is to reverse each word individually. Here, since the array contains only one word, we reverse the entire array again. Calling reverse 0, 4 swaps the first and last characters, making the array H-L-L-E-O. Then, the second and second to last characters are swapped, updating the array to H-E-L-L-O. With no more swaps needed, the array is now restored to its original order, hello. This is also the final output for this example. Now let's explore a more complex example with multiple words separated by spaces. The input array represents the string, the sky is blue. The first step is to reverse the entire array. By calling reverse 0, 14, we begin swapping characters from the start and end of the array. For instance, the first and last characters are swapped, resulting in EHESKYISBLUT. This process continues with pairs of characters being swapped, such as the second and second to last, the third and third to last, and so on. Once all the swaps are complete, the entire array is reversed, and it now reads as YULBSIYKS8. After reversing the entire array, we proceed to reverse each word individually. To do this, we iterate through the array and reverse the characters within each word, delimited by spaces. First, we reverse the characters from index 0 to 3, which corresponds to the word blue. This updates the array to B, L, U, E, S, I, Y, K, S, E, H, T. Next, we reverse the word as by calling reverse 5, 6, giving B, L, U, E, I, S, Y, K, S, E, H, T. Similarly, we reverse the word sky by calling reverse 8, 10, resulting in B, L, U, E, I, S, S, K, Y, E, H, T. Finally, we reverse the word the by calling reverse 12, 14, which updates the array to B, L, U, E, I, S, S, K, Y, T, H, E. At this stage, all words are in their correct order, and the array represents blue as sky, which is our final output. Lastly, let's consider an edge case where the input contains a single character. Here, the input array represents the string A. The first step is to reverse the entire array, but since the array has only one character, calling reverse 0, 0 results in no changes. The array remains A. Next, we attempt to reverse each word in the array, but since there are no spaces and only one character, no further changes are needed. The array remains A, which is also our final output. This example demonstrates that the algorithm handles single character inputs gracefully without unnecessary operations. To analyze the time complexity of this solution, we break it into two key steps. First, the entire array is reversed. This operation involves swapping elements in place from the start to the end of the array. Since each element is visited exactly once during this process, it takes n time, where n is the length of the input array. Next, the algorithm reverses each word individually. This step begins by identifying the boundaries of each word in the array and then calling the reverse function to reverse the characters within those boundaries. In the worst-case scenario, every character in the input array belongs to a word, meaning each character is processed twice, once to locate the word boundaries and once to reverse the word in place. This also results in n time. When we combine the time complexities of these two steps, we get n plus n, which simplifies to n. This shows that the solution is linear in time complexity with respect to the size of the input. Now, looking at space complexity, the algorithm is highly efficient as it operates entirely in place. This means no additional data structures are used to store intermediate results. The only extra space required is for the variables used in the reverse function, such as start and end, which are constants. Therefore, the space complexity is 1. Additionally, whether the input consists of a single long word, multiple short words, or even an empty string, the algorithm performs the same operations, reversing the entire array and then reversing each word. This consistency means the time complexity remains n, in all cases best, average, and worst. Even under the worst-case scenario, where every character in the array must be processed twice, the complexity does not exceed n, ensuring the algorithm is robust and efficient across all possible inputs. When comparing this solution to a naive approach, the benefits of in-place processing become clear. A naive solution might involve splitting the string into words using a method like Python split, which takes n time, while also requiring n space to store the resulting list of words. Reversing the order of words would then take k time, where k is the number of words, followed by joining the words back into a single string, which takes n time and additional space. In contrast, the given solution avoids these intermediate steps and their associated space overhead. By performing all operations in place, it achieves the same n time complexity but with a significantly reduced space complexity of 1. Mathematically, the total time complexity of the optimized solution can be confirmed as n plus n equals n, since each character is processed exactly twice. Furthermore, with no additional data structures used, the space complexity remains 1. This makes the solution not only time efficient but also space optimal when compared to naive methods. When working on this problem, there are several common pitfalls to be aware of. First, not handling extra spaces correctly is a frequent mistake. For instance, if the input string has leading, trailing, or multiple spaces between words and you don't account for these, your output might include unexpected spaces. For example, reversing hello world without trimming could result in world hello instead of world hello. Second, remember that this problem typically requires in-place modification of the input array. Creating a new array or string to store the result might work in a coding exercise but would likely fail an interview scenario where the in-place constraint is emphasized. Another error is reversing the entire string but mishandling word boundaries during the second step, which can lead to misplaced spaces or incorrect word order. Edge cases are also critical to consider. Inputs like an empty string, a single word, or strings with only spaces should always be tested. Finally, keep your implementation efficient. For example, using nested loops to split and reverse words can lead to an O, in superscript 2, time complexity, which is suboptimal for large inputs. Always aim for an O-N solution here. Now, let's talk about the insights that can help you excel in interviews. A key approach for string manipulation problems, like this one, is the two-pointer technique. This method is particularly effective for reversing words in place. By using pointers to identify word boundaries, you can reverse substrings efficiently without additional space. Another important pattern to recognize is that problems requiring in-place modifications often hinge on careful index management. Being meticulous about how you handle indices ensures that you can modify arrays or strings directly, avoiding unnecessary space allocation. Lastly, communication is just as important as your solution. Make sure you clearly articulate how you plan to handle spaces, edge cases, and constraints during the interview. Interviewers are often more interested in your reasoning process and how you address potential challenges than in just the final answer. This problem is closely related to a number of other string manipulation challenges, and studying these can deepen your understanding. For instance, problem 151, reverse words in a string, is very similar but focuses on reversing the word order while also removing extra spaces. Then there's problem 186, which is the one we're discussing, reversing words in place within a character array. Problem 344, reverse string, is a foundational exercise that helps develop intuition for using two pointers to reverse strings efficiently. Lastly, problem 557, reverse words in a string 3, takes a slightly different twist. It requires reversing each individual word in a string while maintaining their overall order. Exploring these problems can strengthen your grasp of the patterns and techniques needed to solve string-based challenges effectively. Finally, let's explore some alternative approaches to solving this problem. The two-pointer approach is a popular and efficient method. Using two pointers, you can identify word boundaries and reverse each word in place. This approach is highly space-efficient, requiring O(1) additional space, and runs in O(n) time. However, it does require careful management of word boundaries to ensure spaces are preserved correctly. Another option is using built-in string methods. You could split the string into words, reverse each word, and then join them back together. This is simpler to implement, but it uses additional O(n) space for intermediate storage, making it unsuitable for problems that require in-place modification. A third alternative is to simulate the split and reverse process manually. This involves iterating through the array to identify word boundaries and reversing words as you go. While this avoids the extra space used by splitting, it can be more complex to implement because you have to carefully manage the indices and boundaries. Each approach has its trade-offs, so choose the one that best aligns with the problem constraints and your implementation goals. Great job! Today, we explored the reverse words in a string 2 problem and discussed the brute force approach. Remember, understanding the basics is key, and optimization comes with practice. Thanks for tuning in. Don't forget to like, subscribe, and keep solving. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!